Now that we've seen a little bit about the basics about how a confidence interval is built, let's talk about the confidence level just a little bit more. So a confidence level is the percentage of all possible samples that can be expected to include that true population parameter. So in other words, if you took a scoop of beans and another scoop of beans and another scoop of beans and another scoop of beans and did it over and over and over, your confidence level is what percentage of those samples would have that true population percentage or proportion or parameter inside. So let's look at the confidence level in the interval above. So in the interval above, they state right here that it's 95% confidence. See that right there? Okay, so that means that we have 95% confidence right here. All right, so then what is alpha? Alpha is the complement. See how it's 1 minus alpha would be your percentage of confidence? So that means that alpha is your complement. So let me put that in there. Let's give me a little bit of grief. There we go. All right, alpha equals the complement of confidence level, often called the C level. Get it? C level. Yeah, they do that a lot. That's as an abbreviation. So it's the complement of your confidence level, which means that in this case, alpha is equal to 1 minus 0.95, which would be 0.05. That's your confidence level, and then you take it away from 1, and you have your alpha. Now, alpha has a meaning that's actually quite important to us, and we will learn about it in chapter 10 a bit. So for right now, just know that it is the complement of your confidence level and that it's coming back to haunt you, how important that is. All right, now what would happen if we we keep the data from our original scoop? So you don't change scoops, you don't take a bigger scoop, you don't do any of that stuff, but you want to raise your level of confidence. So I did that, and I got it right here. Again, you don't really know where the numbers came from, so bear with me here, but it would go from 14.8% to 35.2%. Now I have in here the pink right here. That was the old confidence interval that went from 17.3 to 32.7 right in there. So you can see that it makes the interval larger, right? So it raising the sea level but not changing anything else makes the interval larger. The downside to this is that you can make the interval so large that it actually is meaningless. So let me make a little. Right? You can make the interval so large it's useless. For example, I am, let me just give you the example. e.g., we are 99.9% confident the proportion is between 10% and 50%, something like that. It's like, well, yeah, you're really certain, but it's useless, right? Because, I mean, how good is it for you to think it's between 10 and 50? Actually, 10 and 50 wouldn't work for this one. It'd be 10 and 40, right? So 10 is 15 away to the bad, and then 15 away to the good would be 40, right? So that's a huge window. You know, I think that somewhere between 10% and 40% of people think this. That's just huge, right? It's useless. Useless. Right? Okay, so how could we raise our confidence level but without that downside, right? What could we do to make it so that we are more certain, but we don't have this huge window for where the true proportion is going to fall? And that would be to take a bigger sample. i.e. A bigger scoop or more scoops, right? More scoops will sometimes do it. So instead of, for elections and stuff like that, they don't take, you know, a poll of 5,000 people. What they do is they take a poll of 1,000 people 5 times, right? So this would be a bigger scoop, like a poll of, you know, let me just make it up, 5,000 people, or more scoops, right? Poll 1,000 people for 5 weeks in a row. And that's actually, the latter one is what they tend to do more often with, for example, political polling and stuff like that. If you do this, if you take a larger sample, right, either by taking a bigger sample in the first place or by taking more samples, right, that'll work. What will happen is that it lowers the sampling error. It'll make your standard error of your p-hat smaller, and that's a good thing, right? Because if you're taking a larger sample, then it's going to vary less from sample to sample, right? So you make your smaller. Okay. The problem with this, of course, is time and money, right? It's all well and good to say, oh, I need to poll 5,000 people. I mean, let's just consider our bean box for just a second. Taking a little scoop like this size was not a big deal. Like, I take it out, I can count it, no problem. But if I took out a scoop that was the size of a big gulp from, you know, or whatever, some huge 44-ounce thing from your nearest gas station, it would take me forever to count that. And that's true even if it's not a scoop, even if it's not something as simple as a scoop, even if it's you calling up people, because somebody has to be paid to call 5,000 people, right? And you might not think about it, but it takes a long time to talk to 5,000 people and ask them all the questions you want to ask, right? So it can take a lot of time and money, right? It takes a long time to call 5,000 people, right? That's why they do it 5 weeks in a row. They don't do it because they don't think a poll 5,000 would be a good thing, although it has its issues. But the bigger problem is that nobody's got the money to pay for that. What they do is they do a poll of 1,000 people 5 times, right? That way you get the numbers that you need, but you can do it in a way that's reasonable in terms of time, because it actually takes a long time to call that many people. The one thing you're going to have to be careful, also note, you must be careful to make sure that n is less than or equal to 5% of your capital N, right? That your sample size is less than 5% of your population size. This isn't a problem for something like, you know, all of US voters or something like that, because if it's talking about all US voters, this number is so large that of course this is, your little n is small. Not a problem. But if you're in a small district, for example, you wouldn't want to poll that many people, because what's going to happen is you will lose independence, right? Otherwise, you will lose independence. And independence, remember, is always an important thing. We always want to assume that we have a random sample that is independent and unbiased, right? And if you get bigger than 5% of your population size, then you're going to lose that independence that we rely on so heavily. This was noted in section 7.2 or 8.2, excuse me. There, I kind of brought this down here because this is another problem. So the problems are time and money, and you got to be careful not to do so big a scoop, so big a sample that you lose independence, right? And that was in section 8.2 that we learned that, right? So then the question becomes, well, what do statisticians really do? Like, how do they raise their confidence level? And the answer is, it depends, right? It depends on the time and money available, always, right? It also depends on, hold on, I realize I don't want that there. Depends on time and money available, and also depends on the error level that the people can live with, right? Right. So for example, let's say you were interested in the percentage that are going to give away Halloween candy. That's a small deal, right? So you can have a small n and a large error are okay. And the example I gave was what percentage are giving away Halloween candy this year. Okay, it's not that big of a deal if you're off by quite a bit, right? It's not the end of the world. I mean, the candy companies won't be thrilled with you, but you know, everybody will survive. Whereas if it's a big deal, then you want a large N and small error. So for example, let's say you want to test a new drug, for diabetes, or something like that. That you'd want a large N because you don't want to have a big error. You want a very small error, right? Now keep in mind what we're talking about here isn't really particular to section 9.1. A lot of what we're discussing through this whole example is talking about stuff that's true of all confidence intervals through the rest of the course. And you're going to see confidence intervals in chapter 9 and chapter 11. So just keep in mind, that's why I'm spending so much time on this example, because I'm actually setting up a lot of ideas for what's going to be needed for later on. Okay. Speaking of which, let's stop right here and we'll finish off this example, I swear it, in the next video. So let's pause and I'll see you back.